All right, good afternoon. Good to see you guys here. I know it's the last session of the day, but I'm really happy to see so many of you show up. So my name is Stephen Sitt. I work for IBM in the San Francisco Bay Area. For those of you who don't know, we actually have a lab, we call it Silicon Valley Lab, as well as Armadan Research in the area, in Silicon Valley. And for the past 3.5 years, we've been working on big data related capabilities. We have a Hadoop-based product. It's called InfoSphere Bay Insights. And we have other capabilities surrounding it as well. So today, obviously, I'm not talking about our products. We've been actually working with many customers over the years, and the analytics is obviously a key topic, and we hear a lot of requirements on R. So we've been working with our colleagues in research. We've been looking at open source, and we developed a new capability today. So I'm really hopeful that I can present you about what it takes to run R in Hadoop, and the different approaches, the pros and cons of these different approaches. And also, I'm hoping to impress you with our new capability, which make running R in Hadoop a lot easier than before. And the capability is called Big R. So that's really kind of the agenda today here. Excuse me. I first will cover a couple of high-level charts very quickly, the rationale, why run R on Hadoop, the basic requirements, the different approaches. I'm going to touch on R Hadoop a little bit because that's been there for a little while. And then I'm going to quickly get into the introduction on Big R packages that we just introduced in our new release. And what I would do is I would try to show you a demo on the basic aggregation, summarization, of data that is in Hadoop, as well as show you some of the capability that we're working on in terms of very large-scale data mining technique, especially dealing with very sparse data sets that you typically work with things like a sophisticated recommendation engine for your applications. So that's basically the layout of what I'm going to talk about today. So rationale, right? So you guys know about this. You're not new in working with R and working with Hadoop. This is what we hear from customers all the time, that they want better productivity, first of all, right? And because the data scientists there, they have a lot of R skills that they learn over the years in graduate schools and universities. And when they enter the workforce, they want to continue use R as the language. So believe it or not, when we work with customers, a lot of time they're telling us that, we are, the enterprise, and we're holding this infrastructure for our users, who are line of businesses and data scientists, but they prefer to work with R. And a lot of time when they develop these R algorithms, they come to us, and we have to port it to some other languages in order to make it run on our infrastructure, including Hadoop. And that certainly take away a lot of productivities, from the overall users. And the other reason for this is, as we all know, there's a huge amount of open source packages that's available out there. So data scientists obviously want to leverage as much as they can, and also able to customize these algorithms based on their specific need. The second reasons, the rationales on running R on Hadoop, is what we call the platform for the next generation of analytics. And this is important because this morning, in the keynote speech, we heard about different concepts, about data lake, about data landing zones. Some of our customers call it the sandbox, right, for analytics. So really, a next generation of the infrastructure needs to take the consideration of how you get all the data in and provide analytic, right, on top of the data that's in the standard platform. Right, so this concept about moving the analytics into the data versus moving the data out to the analytic is a key reason also for running R in a platform like Hadoop. So we talk about big data. Certainly, scalability and performance is obviously the key. Otherwise, it's perfectly fine just running on your laptop computers, right? So when we talk about scalability and performance, we talk about the size of the data. That's certainly important, but also the number of variables. That's extremely important as well. So we want to be able to open this up so it's much more scalable environment for data scientists so they don't have to take too much consideration in terms of the memory consumptions, in terms of random sampling the data, and so on. Scalability. Customization, I mentioned that earlier. There are a huge amount of packages out there that they want to leverage, but most of the data scientists, they don't want to stop there. It's not like they take a particular module, they can run it, and they're fine. They always want to open up the hook and fine-tune it, right? So the ability of leveraging what's out there is important, but also it's equally important to offer, a set of API, if you will, so that the data scientists can actually use native R language to develop the algorithm that best fit their business need. So I think we probably all agree to these, very basic rationales of running R on Hadoop. So let's take a look at the common pattern here. We've seen some of these earlier this morning in the keynote. I think this is my version of it. Hopefully you will like it. I'll go over it very quickly. So as we all know, we have all kind of data, structured, unstructured, inside the firewall, outside the firewall, coming in, and there's various method of getting data injected into what we call the data lake, data landing zone, analytics sandbox. The idea here is to get the data in the relatively original format, in typically what we call the right optimal format, so that you can run a set of data transformation, data aggregation, summarization using some language that you prefer. Some people want to use Java, Pig, and some other languages as well, or some people prefer to use a GUI-driven tool. So there's plenty of those that's been available in the market, such as Data Mirror, and from IBM, part of our product, we call it Big Sheet. So those are all good, and it's doing transformation, getting data sometimes into a read optimal format, for example. But at the same time, the analytics are critical, right? So here, without doing the data transformation into a more structured form, you want to make it available for your data scientists so that they can come in and slicing and dicing and build models directly on the data that is natively sitting in the landing zone, right? Particularly in Hadoop. So once the analytic is done, sometimes it's introducing new attributes, dimensions, and so on into a more structured form. They can be obviously in columnar stores such as Edge-based, but also you'll be able to define search indexes. Some of the talks are talking about Lucene and Solars. You want to be able to make the data sets available for search, as well as you want to make the data sets, the end result of these analytics, if you will, available from front-end relational databases or your data marts or your MDM system, for example, if you have acquired new knowledge about your customers and enable some applications such as the next best action and so on. Right? So this is kind of like a very high-level picture, kind of put all things together as a pattern. So again, very quickly on R. Again, this is nothing new. I just put it up here to kind of level set. We all know that R is a very popular. It's a scripting and interpreted language. It's open source. It's free. And as I mentioned earlier, there's a lot of packages out there, and it's the de facto language for data scientists to do statistical analysis, to actually build descriptive and predictive models, and so on. And it's also, there's tons of visualization packages that's being developed and made available. And we are sometimes fairly commonly to see that our customer actually develop what they call production-ready reports, right? Sometimes in PDF and other formats, right out of using R, for these visualization packages. So certainly it's emerged as also a potential competitor to some of the more traditional way of doing analytics as well. So R is really hot. It's quite lean, right? It runs really well, and it's free, as I mentioned, and also it's state-of-the-art. So there's a lot of new algorithms every day is being developed. So we've seen very often from our colleagues in research, they've been working with the universities. A lot of professors, when they work on a new problem in the machine learning world, for example, they haven't write their paper yet, so they get the R implementation as what they call the reference implementation out first, right? So anything you can pretty much think of, there's an implementation likely that you will find in the R open source community. So it seems like I'm selling a lot for R. I don't really have to do that. You guys know about this. But what's the bad news, right? The bad news is that R is unfortunately not built for big data, right? So the working model of this is that you're working with the data set, which is persisted somewhere, but you need to bring that into memory, right? As soon as you bring it into memory, then you can use the language and work with the data set. So what does that mean? That means it's bounded by the amount of memory that you have from a scalability standpoint. So it's not natural for working with a distributed scale-out system like Hadoop, right? So again, the problem is not new, it's well known, and there are many different approaches that people have been working on enabling R on Hadoop, and it's been a while. Many of our customers and they are using it, and some of them are in production. A common approach, which obviously has been around for many, many years, is just to basically leveraging the MapReduce framework. Whereas when you write a MapReduce application, you can use languages other than Java. So in this case, you can use not only Python, you can do that, but you can use R to implement your mappers and reducer functions. So it works, but it takes fairly careful implementation, right? Not only you have to know about statistics and machine learning, data mining, but you also need to know basically the paradigm of how MapReduce work. You have to take care about the input data types, the output, and how data is constructed for the mappers, and how they're grouped into the reducers and produce the right results. So it's fairly complicated, although it's very much doable, right? So there are other efforts that actually make that programming slightly easier, right? So a good example of that, there are many different approaches, but a good example is R Hadoop, right? It's also fairly common. It's driven by the Revolution R teams, and it's basically a set of APIs. So first of all, they have the APIs that encapsulate things like data access from Hive, from HDFS, from HBase, so you can get data in. And then it offer a R API, if you will, on top of MapReduce programming. So the benefit of this approach is you can work in the native R syntax, but the drawback is you still have to use relatively low-level API that you do have to implement. Here's my mapper, here's the function that go with the mapper, as well as the reducer as well. And I will give you an example on exactly how that actually look. There are other approaches. The latest one, which is obviously very interesting, I think there's a fair amount of coverage on Spark from the Berkeley lab. And there's also a new project which is called the Spark R, which is basically, again, a R package API set for RDD data structure that's running in Spark, which is fairly new, but is very promising. And we've been very actively looking at that approach as well. Other than that, there's a couple of fairly old, more legacy approach. From IBM, we also have a language called Jackcode that we open sourced a few years ago, and there's a Jackcode to R bridge where you can actually write Jackcode and getting the data that's more JSON format natively. And then in that Jackcode script, you can also embed a R script in there, and behind the scene, we convert that all into lower level MapReduce job to run it on the Hadoop system. The other approaches that's highlighted here, like Scalar R from Revolution and some of the other approach are not really Hadoop. They're more considered as the legacy approach of running R in the distributed environment. Okay, so let's drill a little bit deeper on R Hadoop before I introduce some of the other capability. So here the best thing to explain this is to show an example, right? That's what I'm going to do when I talk about the big R. I'm going to actually show you a demo instead of just talking on all the slides. So an example here is you have a set of airline data, which is common with all the demo using R, and a very a simple analysis here, like determining the mean, of the departure delay for by airline and also by month, right? So this is fairly simple partitioned type of analysis. So how do you actually do it in R Hadoop? Again, as I mentioned earlier, you do have to provide your mapper functions and reducer functions, but it's fairly simple. There's API. Like, for example, you can read a line from the input text format. That consists of basically one row in the input data that the mapper gets. Instantiate that as a vector in this value variable here. Then you construct the key value pair, right? You do need to have a key value pair here to work with the mappers and reducers. The key obviously will be the carrier, the year, the month. The value will be the delay departure for each of the flights, right? As your input data. Then the normal Hadoop things will pick up, do the sorting, do the shuffling of the data, hand it over to the reducers. At that time, the reducer would call the mean function, the package from R, and it will calculate the mean value for the delays for each of these partitions by month as well as by carrier. So fairly simple flow. As you can see that the code, it fit in one page, so it's pretty nice, very doable. But again, I just have to highlight that the only thing that might not be that natural for a typical data scientist standpoint is that they will have to understand, what is a mapper and a reducer and how do I deal with data that way and passing around the data. Right? So that would be the thing here. So that's on R Hadoop. So now let me introduce a new approach, and we call it Big R. The reason we call it Big R is that in our efforts around Hadoop, we have a set of analytical capabilities that sit on top of pure Apache Hadoop. That's what we call. And we have a naming convention where Big Sheets, Big R, Big SQL, and so on. So this is one of the newer capabilities that we provide in our product. So at the very high level, it provides three capabilities, right? The first one is, again, it's very important to consider that the data is native data. They can be in sequence files, in basically text files, can be in aerial format, which is getting more and more adoption out there because of schema evolutions and all the benefits there. So data stays in Hadoop, in the data lakes as its native format. So what we provide is a set of packages, right? We call it Big R packages. And once you load that into R, and I'll show you the demo later on, then you can start working on things like getting the basic aggregations, partitioning on the data, doing statistical analysis on the data sets, right? And also very important, this concept about partitioning the data, right? That's number two, scaling out R. Well, we provide the API to help you to partition the data. And then for each of these partitions, you can use a very common way in R is apply as well on a function. So you can define a function in R using what we call a group apply, and then you can internally we package up all these data and push it over to the R installation on each of the data nodes, so that we can do this analysis as well as building models in parallel on all the data nodes, so leveraging all the scale out capabilities. So that's case number two, which is very important when you say you want to build a model. The example I gave earlier about partition by dates, by airlines, but when we work with customers, it's very common that they want to build model based on a particular customer segment, for example, and easily you can get to 100,000 models or even more that you need to build. And from a statistical analysis standpoint, you want to also do things like feature selections. So there's a lot of problems that actually can be partitioned, and this is a very handy way of leveraging the packages out there in R. The third capability, which is that there's going to be a class of problem that is that you do want to build a model that's on the entire data sets, right? And further partitioning the data, running smaller models, even with techniques such as ensemble, it doesn't help you from accuracy of the model, right? So in fact, building on the big thing is actually more accurate. And a good example of that would be the recommendation engine, right? When you're dealing with extremely sparse data sets and you want to build things like similarity on the product, similarity on the customer behavior, those are the cases that you do want to use true distributed machine learning capability. So we have that in this big R model as well, which I would go over. So in the next few slides, I just going to go through the slide very quickly. And I think, again, showing code is kind of boring, so I would just basically go right into R Studio and show you some demo. Before I do that, I just quickly, again, introduce the airline data set, which some of you might already seen from many different demos out there. It's actually a handy data set you can download from the US Department of Transportation. It's got all the histories. For 22 years, every single flight is logged in terms of the origin, the destination, the flight time, the delay time, and things like that. And these are basically a dump of the different columns, data types of the data set here. So the first scenario that I'm going to show you is the case number 1 that I mentioned earlier. The data is in Hadoop, right? And using a conventional R tools. This can be anything, but R Studio is a common one out there. You can connect into Hadoop. You can do browsing of the data that's on HDFS. For the data that you want to analyze, you can bring that in and instantiate a set of variables, and particularly that we created for the big R package is basically three things, right? There's just like the R frames, which is commonly used to work with a table. We have a big R frame, so it's a big R implementation of frame, and then there's a big R implementation of a vector and also a list. So those are basically the 3 things, very, very simple. And the difference for those 3 things compared to a standard R function is that we don't bring data into memory at all. So it's simply imposing a structure or a schema, if you will, on the data, so R knows how to work with it, or big R knows how to work with it. So once we have that, then we can slicing and dicing the data. We can transform the data using conventional R. We can produce graphs, and those are the things that I'm going to show you. The second concept that I'm going to show you is that when you're working with this data set, when you're creating groups, you're partitioning the data, and then you can apply a functions, or you can apply any of those R packages out there. Let's say, for example, you want to build a regression model for something, right? And the demo that I'm going to show you is a regression, is a decision tree. I can show you how easy it is to actually build it with this model here. So let me switch over to a demo mode. Just bear with me a little bit. Okay. All right. So here I am in basically the R Studio, and all I have to do is to load the big R package, right? So one line, load the package in, just like any other packages that you work with in R. You can then ask, what is big R? What are the functions that you can use, all with standard R way, and this will tell you, these are what I mentioned earlier, the big R frame, vector, and list, and you can look at the documentation here, and then you can set the local working directory here. And so first thing that we do is let's connect to Hadoop and browsing on some file. By the way, you can see in the back, right? I know it's a little bit small, but. Okay. All right. So let's connect to my VM here, and passing in the username password. By the way, the password obviously can be encrypted. So all I want to do as a data scientist here is I want to slice and dice this data, finding some basic statistics, such as things like variance, standard deviations. I want to look at some correlations between the columns. Then what I want to do, as an analyst, I want to build a model so that I can predict future delay, right, for a given set of flights for the airlines. So those are the sequence that I'm going to go over. So now, since I'm connected to Hadoop, I can do a file system browse and see what's in there in my HDFS. Specific directories, and now let's bring a data sets into big R. So in this case, I know that there's this file that's sitting in as a CSV file in HDFS. I use the big R frame to instantiate that. And here is a handy thing. So in the case here, I have a parameter called use.MapReduce. In here, I equal to false. That means that I'm actually working. I know that I'm working with a very small data set here, right? So there's really no point of instantiating the overhead of MapReduce, and I just can work directly with the data. So I can set this true. Then every single operation that I do with R will then be translated into a MapReduce job and running in the cluster. So I've connected using false, and it's warning me that it's actually not going to be running as MapReduce job. So make sure that you have enough memory and all that things. So let's explore the metadata. So I just use a simple str function on the new air variable that I instantiated as a big R frame, and you can see that these are the columns, and you can see the data type. You can see the first 5 sample data sets, first 5 rows in this data sets. If I want to say, okay, how many number of rows out there? Very simple. You use the conventional R n rows, passing in the variable. You can do a count. You can see the number of attributes in this data set. You can attach air into the path in R, so you don't have to specify the specific path for this variable every single time. So let's do some basic summarizations on this data set. So here we provided a summary function, which is actually very handy because now again, right, the data is not in memory, it's sitting in HDFS. We have a set of basic functions like min, max, and standard deviations and things like that you can use, but also you can define your own function. These are in the relational words more like column functions that you can define with any formulas out there, and you can instantiate that and then use that as a summary. So that will produce that as well. So very handy from data exploration and summarization standpoint. And then once you have that, you can see the distribution of the flights over time using the barports graphic libraries. You can do it based on airline, right? See all these simple functions, basically they will just work. And then you can do drilling down, you can do projections, you can do selections by applying predicates and things like that. So in this case, let's say I'm only interested in the flights that were delayed, right? So it's adding a predicate into air, which gave me a new variable in R. So very, very easy to do that. And once I do that, then I can compare to say, okay, out of the entire data sets, how many flights are actually, what's the percentage of flights that actually were delayed? Right, so in this case, one line, you can see that there's about 22% of the flights that were actually delayed from the original schedule. You can do further projections and say, okay, now on the entire data sets, and I'm only interested in looking at 2 airlines, the Hawaii airline, as well as the Delta airline. So you can do actually in this case, I'm only looking at Hawaii airline, put that into a new variable. Now I can see, okay, what's the delay for a percentage of delay only for Hawaii airline, right? Again, one line of R code here, you can say, okay, it's about 7% of delay, so that's probably what you would expect it because Hawaii airline is typically flying between the West Coast and Hawaii, where the weather is normally good. So shorting and acquisition on the data, very easily done. You can assign that to a shorting function on the R frames. You can see the first few lines of the aggregates. You can apply that any function in here. You can mix with R function that you implement or using one of those that's been provided into a new function. And then you can then apply it to the summary API. Then in this case, it would tell you the mean distance as well as the mean flight time for all these shorted columns. And then you also can build a visualization out of this. In this case, I'm building up a heat map, and this is actually a fairly nice package that you can, can actually see. And interesting data set here, there's actually one date that actually no flight was happening in US. So you can actually see all of this with the visualization tools fairly easily. Okay. So let's take an example of building a predictive model, right? So I'm exploring my data, with a statistic standpoint. Let's say I want to find some correlation between the columns, so I can find out what are the relevant independent variables that I should use to build my model. So all of these things you can do it in R, right? Without worrying about mappers and reducers and so on. So in this case, again, I'm looking at a subset of the data, a partition, I should say, of the data that's in Hawaii Airline and United. So I want to build two models in parallel for predict the delay for these two particular airlines. So I can do that with a selection here. Preparing the modeling, I find out the correlation coefficients about these particular columns. Would display right away. It's very easy to do. And obviously, it's a demo data, so it doesn't really mean that much. But as you can see that, you find the correlation, it's fairly high between the arrival delay and departure delay, obviously, right? But the other thing is that, you can see that the distance from between between these flights, there's actually not that much correlation, against the other variables. So this will be the typical thing a data scientist would do, exploring the data, really figure out what are the columns that I actually should use to now further building my analysis or building models. So very easy to do the correlation. You can pop that using a standard R visualization package. Again, see the correlation between the different columns. I do a little bit faster here. Typically when you build a predictive model, especially for supervised learning techniques, you will do a partition of the data. A large portion will be used for training, the other portion will be used for testing, and then when new data set come in, you will do scoring. So those are the 3 steps that I will show you how easy it is to do this. To break up the data into the data set, 70% I'm going to use for tests, training, and 30% I'm going to use for tests. Very easy. 3 lines of code. I get the data basically partitioned and assign it to new variable here. I now define the function. So in this case, what I have decided to do is to use a conventional R open source package from the very popular RPark, the regression tree package that actually many people use. It's a really good package out there. So there's like random forests and trees. And in this case, I'll just show you a very simple decision tree. So as you can see here, as part of the function, I'm going to use the standard RPark library. I define that as the library that I'm going to use. I put in the independent variables in here and also the predictor. That's going to be the output of my model. So now I am going to simply run the model itself. And now, because it has 2 partitions, so it's actually behind the scenes going to generate 2 sets of jobs running in parallel in the Hadoop cluster. So imagine that if you have a 100 partitions or hundreds of thousands of partitions, You can do that. Now you have a much larger clusters, but things will happen in parallel. So that's really the handy part of this. So once the model is built, the system will automatically put that into persist the model itself. All the coefficients and all that are there. They will be in HDFS. And now if you want to work on it, then you can pull the data back into the R memory space. So we have a API set here called big R pool. We get the model read back to this R variable here. And then you can then see the visualize the tree that we just built. I apologize, the low resolution here is not very seeable. But I think you get the idea. So then you can run, you can testing the model with the test data sets here. It's the same approach that when you were running, just gonna go through this real quick here. So it's actually the same approach that you're going to do with scoring as well, the same when you're testing the data set. So the idea here is, first of all, the data set is partitioned, so you can run these scoring functions in parallel, but you can further parallelize them, right? Because now for given partition, for example, you're just doing scoring, you're not really building any new models in there. So you can actually use a function here that I showed you earlier that generate a random just use a random number, right? So I want to further generating a random number set of 2's assigned to each of these rows, and then I can then further partition based on this random number I generate for each of these rows, and then I can further push it out for scoring in parallel. So this one, the scoring now is done, and then I can persist the data back into my HDFS as well. So hopefully you see how easy it is. Everything is in R. I don't have to understand what mapper and reducers as a data scientist standpoint. I just use a set of fairly simple API, and then I can work on exploring the data, summarizing the data, as well as leveraging the packages out there so I can actually build predictive models as well on the data. Excuse me. So let me switch back to my charts. So again, here is a summary of the functions that we have in the big R package. I went through some of these demos. It's just rehashing the summary here. Has to do with connections, the three data types. The frame, the vector, the list is really important. Once we bring those data in, we can run exploration. With all these functions. We can do selections and projections, and also all the operators, as you can see, are supported here, and a whole bunch of what we call the table functions as well as sampling, and you can also leverage the visualization techniques out there. Very quickly, you can do the summary function that I showed you earlier is very, very handy. We have a set of functions that's built in, like min, max, and standard deviation, variance, those you can use, but also you can define your own column functions, if you will, that you can use it in here. You can do correlations as well, but the important thing here is in the middle, there's the group apply. So you partition the data, you're defining the function that I showed you earlier, and you run the group, each partition of the data, push that into R, so modeling can happen in parallel. So similarly, we have a row apply that not really partitioning on the columns, but a given set of rows, or you can actually run on all the rows in the table as well. So there's other things like debugging capabilities as well. So one example here. Again, a quick comparison between the approach of R Hadoop. Remember that I covered that earlier, that you do have to implement the mappers and reducers. So here's a good example of a simple one, which is basically the same data set. You're trying to find out the average gate-to-gate times for each of the CD pairs, right? So you do have to, not really seen here, but there's a set of the mapper functions will deal with how to come in the data. You have to do the pairing the right way, and then push it to the reducer. So it's not a whole lot, but it's a fair amount of fair amount of code here, and with the big R approach, it's basically 4 lines of code. Right? So I'm really hoping that I'm impressing you guys on this. But I'm pretty excited about this. 4 lines of code. So you bring the data into R variables. You do a new two new virtual columns here to normalize the city, 2 city pairs in 2 lines, and then you use the summary functions to pass it in all these min, max, and things that you want to do, and then you get your results. Right. So what are the use cases that's actually good for this big R approach, right? So obviously from the productivity standpoint, what I mentioned earlier, from a performance standpoint, scalability is also very important. But one very key important concept that I think all of you are familiar with this, or you already know, that it doesn't get away from the limitation, the memory limitation that's in the R engine itself, right? So in other words, when you have a very large data set, let's say you have a 10 terabytes or more file, right, that you're loading it in, and you don't have that much memory as the aggregate of your cluster, which is fine. You can work it, with this model as long as each of the partition that you're analyzing using R fit in the aggregate of the memory that you have, not the aggregate, fit into the memory of the particular node that you're actually running on for the analysis. So that certainly is one limitation. However, what we've seen is that almost 80% of the problem that we are working with our customers, many of these problems are actually naturally partitionable. Right? In fact, it's better to partition the data because when you build a model, you don't want to necessarily build a model of everything. You want more fine-grained, more accuracy on the model itself, right? So, and there's other techniques of leveraging, building a lot of models, and then do observations and join the model together. So in these cases, I would say 70–80% out there is very natural to use a capability like that. But it's also very important that you do realize that when you are building a very, very large model with terabytes or hundreds of terabytes of data and even petabytes of data, this is not the approach. We need a new approach behind the scene to deal with these. Particularly, the common one is unsupervised machine learning, where you have the data set which is extremely sparse and large, obviously, but also very, very large. And how do you do things like a recommendation engine based on a similarity analysis on these very sparse matrix, if you will? So that's a class of problem that's not partitionable, obviously, and the only way is to have a truly scalable approach. So that's what we've been working with our colleagues in research, and we're productizing that into our products. And this is just one example of encapsulating all of that bigger model capabilities into the same big R API. So instead of calling it in this example, the second half of this is using group apply, but the first one is if I just want to run a regression model on the entire set, the linear regression in this case, then I can just call the function that we provide implemented behind the scene. We're still using the R library. So these are the SystemML is actually our research code name, but as you can see here, most of the popular algorithms that are implemented, starting from the univariate, bivariate statistical analysis, data mining, right? So the association, the k-mean, as you know, is very, very popular, and you do want to do clusterings sometimes on your entire data sets. I would really say that the dimension reduction, the matrix factorization techniques are really getting more and more popular, and many of our customers will be needing that for their next best action recommendation engine. I'll explain a little bit more detail about what that really means. But there's also the conventional approaches like building trees and building regression models and things like that is also provided here. So let me give you an example of what I actually mean by actually using this capability for dealing with very large sparse matrix and able to do things like recommendation engine. So the best thing about this is, again, put up the Netflix example from a couple years ago. You heard that today's keynote as well. I think the first speaker introduced that. This is obviously, fairly new a few years ago, but, a lot of enterprise now is looking at this so that they can do the same things that the internet-based company are actually doing. So the example here is you have basically people and you have products, and the product in the case here are, Netflix case are basically movies, and then you want to be able to deal with explicit inputs, right? Such as, the ratings. So I like this movie, things like that. And you want to deal with implicit input as well. The implicit input is not so much in this example, but, it's very common that you want to bring in clickstream data, for example, right? So look at the customer, which part of the website they're actually clicking, which product that they're looking at, how much time they spend on it, or even customer history, the transaction data, right, from your operational systems. And these are actually considered implicit data sets because the past history does not necessarily imply the future, right, obviously. So those are the data set that you can actually all aggregate them together. And obviously a typical enterprise, you will have millions of customers and you will have hundreds of thousands, if not more, products. And then what you represent here is, this upper matrix here is very, very sparse, right? That basically each of the rows represent the user actions, the people actions on a particular product. So in this Netflix example, it's just the aggregate of how many of these movies. So imagine that if you run a very large algorithm for similarity analysis, right? This is a very difficult computer science problem. It can take a lot of computing power. One very common technique is what data scientists refer to as matrix factorization or decomposition. So basically what it means is you decompose this very large sparse matrix into smaller matrices. So in this case, a small matrix that represents the similarity with people, and then the other very dense and small matrix that represent the similarity on the product. So in this case, the movie. And you're basically doing a partitioning as well actually I should say clustering as well on the K factors. And the K is basically a data scientist will pick that based on the data set, based on how much storage that they want to store as the end result of this model, as well as the computing time that's needed when a new recommendation needs to be made, right? So when you have a new customer that come in, you need to use this K and the formula behind it, these smaller matrices, to actually calculate the potential new product that they're interested in. So these are all the trade-offs that the data scientists will make. But at the end of the day, you use this capability, do the decomposition, running that as a large batch job in MapReduce. We automatically convert all that into MapReduce jobs. And then when a new user come in, you will typically just maybe interact with just a few products. And then the same technique will be used to factorize that new rows, actions, into the values for the people as well as the K. And then you do the computation there. Now you know what are the potential areas of products that they will likely buy as well. And then you can also do that the same thing for products. As you introduce a new product, you can do the similar analysis. Now you can go back and say who are the people that potentially will be interested in these new product or services that I just introduced. So it's a fairly common technique. I think it's not new news for you guys, but we're definitely seeing more and more, and it's obviously a good demand of able to do these kind of analysis very quickly. And that's one example. The other example that we're seeing very common is what we call the topic evaluations on social media data or any unstructured data that could be coming in from the call center data, but in this case, it's actually Twitter data. So consider every single Twitter feed is get injected into the system, and you basically tokenize. And by the way, we do have text analytic capability as well in our Big Insight products. But basically, you tokenize it. You build this again very sparse matrix that representing all the feeds as all the rows, and the columns representing all the token that you extracted from the Twitter feeds. You use the same technique to decompose the matrix into smaller matrices for document as well as for the different words. So then you can see, very simple on the frequency of word appearance, you can build a graph like this. And then what happens is, as a human being, as an analyst, you can come in, investigate these clusters, these K clusters that you build, figuring out is there commonality. So what are the topic that these documents are talking about? Then you're inferring some meaning on these these K clusters. Then you can, as new documents that come in, you can do automatic classification on the new documents. So that's actually one example of doing matrix factorization using Java. So not a whole lot, 1,500 lines of code. You can do this, but I'm hoping I'm impressing you guys with big R. 5 lines, 4 lines, 10 lines, less than 10 lines of code that you can do this. Since I'm already out of time, very quickly on the summary here. So again, R is very popular in the data scientist community. We really want to enable them to work on big data. There's all this concept about data lakes, landing zones. It means nothing if your analyst cannot work with data that's in Hadoop. There are many approaches. There are pros and cons with the different approach. We also introduced a package called Big R as part of our capability, which basically allow you to slicing and dicing and summarizing the data, but also as a vehicle that we can introduce newer machine learning algorithms that's very useful for dealing with very large, complex problems. Okay, so that's basically my talk. And do we have time for maybe one question, or we can do? No, okay. So if you have questions, then we can have a discussion. Okay. Thank you very much for coming. Really appreciate that. Thank you.